Hearty hello from West Virginia. I guess not. Well, what I do know though is that it is time for Joke of the Day, and I know you've been waiting for Joke of the Day. This is a great one. This is one of my favorites. So why does the 90-degree angle win every argument? Because it's always right. Love a good geometry joke. It always makes my day brighter. Okay, and what does make my day brighter is learning how to solve equations, linear equations, by adding or subtracting. So what we're going to do is we're going to take a look at how to solve equations, very basic equations, where it's only going to take one step in order to solve that equation. And we're going to start with the types of equations where you're going to need to either add something or subtract something in order to solve that equation. Now, before we get into that, we need to understand that linear means that your variable is going to be to the first power. Very important that your variable is to the first power because one, that creates a straight line, but two, these are the, like I said, we're going to start with basic types of equations, and the first power is going to be the most basic type. Notice the two examples that I've got sitting up here. This variable is to the first power, and this variable as well is to the first power. So we're going to be able to solve these fairly easily. The other thing that we need to note before we get into this is what we call the golden rules of algebra, or what I call the golden rules of algebra. And there are two golden rules. And if you can remember these two golden rules, you can solve any equation. Even the really big, very difficult equations, you'll be able to solve every single equation if you can keep these two golden rules straight in your head. And the first of those golden rules says, do unto one side as you would do unto the other side. And this is because your equation is basically like a pan balance. And I have a pan balance sitting here so that we can see what I'm talking about. Pan balance is the kind of thing that you typically see perhaps in a science class. Notice that this pan balance, it's got a pan over here that we will put things into and a pan over here that we put things into. And the two need to be balanced out, or at least we're hoping they're going to be balanced out. And when you have an equation, this equal sign right here, the equal sign, is like this fulcrum that is in the middle of the pan. So I'm going to put this equal sign right in the middle of this pan balance. So what happens when you have your equation, it's like saying that what I have over here is sitting in one pan. And then, and actually let me do this way, let me put it in red to coincide with that pan. So what I have over here coincides and goes in that pan. And then what I have over here, and I don't have a yellow, so I'll go with a purple. And what I have over here goes in this pan. And like I said, this equal sign is this fulcrum that's in the middle. So what happens is, in order to get this variable by itself, and that is the goal when you're solving equations, you want to get the variable by itself with nothing else with it. And so in order to get this variable by itself, I need to do some things to that side of the equation. I need to take a look at this side of the equation. I need to say, well, what would I do to get that variable by itself? And the catch is, because this thing is a balancing act, I want it to stay balanced. Currently it is balanced. Like for instance, you can see that I have a little piece here that's going to represent this X, and I'm going to put it in that pan. Notice it kicks it all out of balance. But now what I'm going to do is it says that I have added 4 individual little pieces to that pan. So I've got 4 individual little pieces right here that I'm going to drop in 1, 2, 3, and 4. And it's still not balanced. But now what it says is, in order for it to be balanced in this pan, I need to have 9 of those individual little pieces. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Oh, that was 8, and here is 9. And you can see that, okay, now my pan balance is balancing out. And that's what this equation says. It says in the red pan is this, in the yellow pan is this, and the two are equal to each other, and that creates balance. So in that first of the golden rules, what it's saying is I want it to stay balanced. So whatever I do on this side, think about this. If I took this side over here and manipulated something to it, it would kick it out of whack. So I have to do the very same thing to the other pan to make it stay balanced. And that is the first of those golden rules of algebra. The second of the golden rules of algebra says, do the opposite of what has already been done to the variable. And basically what that means is I'm going to reverse the order of operations. Now, in order for these two to make sense, let's take a look at the illustration that we have here. So we have our x plus 4 in the red pan, and we have our 9 in the other pan, and it is balanced out. Now, if it's not balanced, if it doesn't look like it's balanced, quite frankly, it's because it's a very cheap balance, and it's not really the world's best. But it should be balanced because I've already chosen those pieces very carefully that they should be balanced out. Now, my goal is to get this x by itself. In other words, I want to know this little green piece here, what does it represent? How many of these little pieces does it represent? Well, in order to figure that out, I need to say, well, I've got to get that green piece all by itself in order to figure out what it represents. I need to figure out what would be in this pan over here to balance out with this to the point where there's only a green piece in there, that x completely by itself, then what would be in this pan to make it all balanced out? The problem is, as you can see in the pan, I have way more than just this little green piece. I have way more than just the x. There's 4 of these individual little pieces sitting in there, so I need to get rid of these 4 individual pieces in order to get that x by itself. So what I'm going to do is I'm going to take them out of that pan. Now when I take them out of the pan, like I had discussed before, notice it's all out of balance now. So when I subtract those 4 out of there, it's all out of balance. And that subtracting 4 is the idea of what I said right here. Do the opposite of what has already been done to the variable. I already took that variable and added a 4. I need to do the opposite, and I need to subtract 4. But in order to keep it all balanced out, when I took those 4 out of the red pan, I need to make sure that I take 4 out of this pan to keep it balanced. So I'm going to take 4 out of the other side as well. And when I take 4 out, here's 1. And here's 2, and here's 3, and take that last and 4th one out, and you can see that, again, if it's not balanced, it's because it's a very cheap balance. It should be balanced out there. And so what that tells me is, okay, my red pan now has that x, that green piece, totally by itself. So when I subtracted 4 over here on the left, that gave me the x by itself. And then in the yellow pan, I had 9 in there, and what I did was I took 4 out, and you can see that when I took the 4 out, what am I left with? I am left with 1, 2, 3, 4, and a 5th piece here. So that means that when I had 9 and I took out 4, I was left with 5 pieces over here. So in other words, this green piece is the equivalent of 5 of these little pieces. And I know that's true because this is worth 5 grams and each one of these is worth 1 gram. So that's how I knew it should be balanced out. But the idea again here is, in order to solve your equations, you do the golden rules of algebra. And you do the opposite of what has already been done to the variable. In other words, you're going to reverse those order of operations, which doesn't make a whole lot of sense right now, particularly because we're just going to start with these one-step equations. And then you make sure that whatever you do on one side of the equal sign, you do on the other side of the equal sign. And that's how you arrive at your answer. Now, how would I check to make sure that this is right? How would I know, okay, this green piece really does represent 5 of those little pieces? Exactly. What should happen is I should be able to say, okay, let's start with what we had, and let's take 5 of these little individual pieces and put them in there. Now let me see if I have 5 of those individual pieces, and in fact I do. Wonderful. So I should be able to go 1, 2, 3, 4, and 5, and it should balance out, and it does appear that it is going to balance out. So I can check and make sure that it's right. So what this means to me is, in order to check this, what I should be able to do is I should be able to take what I found to be my solution. I should be able to substitute it in or plug it in where that variable is. Because again, that equal sign means the two are the same. The x is a 5. So if the x is a 5, then that means I should be able to take the 5 and put it where the x is. And when I do, I get 5 plus 4, and 5 plus 4 is 9. And does that give me a true statement? Because remember, in math, everything is all about truth. Does that give me a true statement? Yes, in fact, it does. Now, when you check it, please understand that this is not what you circled. That's not your answer. Your answer is over here, what you got for your variable. So that's how you solve equations. Do the opposite of what has already been done to the variable and do the same thing on both sides of the equal sign. So let's try another one here. This says m plus 18 equals a negative 57. Well, I want to get this m all by itself. So what has already been done to that variable is adding 18. When I do the opposite, I'm going to subtract 18. And like we noticed here with the pan balance, what I do on one side, I have to do on the other side. So I need to subtract an 18 over here on the right-hand side. Now, that means on the left, that m is completely by itself like I wanted it to be. And on this side, a negative 57 minus an 18, this gets into the sign numbers that we know how to do. A negative 57 minus an 18 would be the same thing as adding a negative 18. Basically, the idea here is the signs are the same. So we're going to combine the digits, and we're going to keep the sign. So my m is going to be a negative 75. And like I said, I can check this. And the way that I'm going to check it is I'm going to take that negative 75 and I'm going to put it where I see that m right there. So negative 75 is going to go up here. And a negative 75 plus 18 does in fact give me a negative 57. So I know, yes, this is right. And my solution that I came up with really is the right answer. All right, so you guys know that I like for you to have a lot of examples. So let's try a few more. Let's flip that board around. I've always got lots of examples for you. Okay, so in this one it says x plus a negative 6.4 equals a negative 11.5. So I'm going to ask myself, what has already been done to that variable? I've already added a negative 6.4, so I have to do the opposite. And the opposite would be to subtract a negative 6.4. So I'm going to subtract that negative 6.4 on both sides of that equal sign, remembering that subtracting a negative is really adding a positive. And these will cancel out over here. That will give me that x all by itself like I wanted to have. And on this side I have a negative 11.5 plus a positive 6.4. Here we are again in those sign numbers. But you know that when you're adding sign numbers and the signs are different, that means take the smaller digit from the larger digit. So I'm going to take that 6.4 from the 11.5, giving me a 5.1, and I'm going to take the sign of the larger digit. So that means I'm going to get a negative 5.1 for my answer. And once again, we can check that. We're going to take that negative 5.1, put it right up in here, and say negative 5.1 plus a negative 6.4. Those signs are the same, so we'll combine the digits. 6.4 and 5.1 is 11.5, and we'll keep the sign, giving us a negative 11.5. So in fact, when we plug it in, we do get truth because the left side and the right side are the same. That tells me, yes, that really is the right answer. All right, let's keep it rolling. So this one says y plus a negative 2.7 equals a negative 9.2. And again, I'm going to ask myself, what's already been done to that variable? We took this y, we already added a negative 2.7. The opposite would be to subtract a negative 2.7, like we saw in the previous example. So when we subtract that negative 2.7, remember that's just like adding the opposite. So when I add the opposite here and here, these will cancel out, giving me that y by itself like I wanted. And on this side, like in the previous example, I'm going to add two sign numbers. The signs on them are different, a negative and a positive, which means take the smaller digit from the larger digit. So a 2.7 from a 9.2 will give me a 6.5. And then I'm going to take the sign of a larger digit. The sign of that 9.2 is a negative. So that gives me a negative 6.5 for my answer. And once again, I can check. Just take that negative 6.5, plug it in here. Those signs will be the same, which indicates add up those digits. So a 6.5 and a 2.7, in fact, will give me a 9.2. And since those signs are the same, I'm going to keep that sign, and I'm going to keep that negative on that 9.2. Giving me truth, because when I plug it back in, the left and the right side are the same, and that creates truth. When it does, then that tells me, yep, that really is the right answer there. All right, we're going to switch gears just a little bit. Notice that this one says a minus a negative 6 equals a negative 3. And I'm going to ask myself, what's already been done to that variable? I subtracted a negative 6. So the opposite would be to add that negative 6. And so I'm going to add a negative 6 here. Now these will cancel and that will give me that a by itself, but I want to show you that there is another way to look at this. The other way to look at this is to say, well, wait a minute, subtracting a negative is really adding a positive, so this would really be a plus positive 6, and the opposite would be simply to subtract 6, which is essentially what happens here. When you're adding a negative, you're essentially just subtracting. So it's all going to be the same no matter how you want to look at it. You can either go ahead and say, well, I'm going to call this add a positive, and I'm just going to subtract 6 here and subtract 6 here. But if you subtract 6 over here, notice what happens. You're still going to say, well, I'm going to add the opposite and add a negative 6, which is what we had there. So like I said, it really doesn't matter how you look at that. So the bottom line is this. That will get that variable by itself like I wanted to happen, giving me my a, and now over here I'm combining up two digits that have the same sign. So when I add up two digits that have the same sign, I'm going to combine the digits. 3 and 6 gives me 9, and I'm going to keep the sign on it. And once again, I know that I can check this. I'm going to take that negative 9 and plug it right in here. Negative 9 minus a negative 6. Well, in this case now, subtract a negative, we do need to look at it as add a positive. And a negative 9 plus 6, the signs are different, so I'm going to take the smaller from the larger. 6 from 9 is 3. Take the sign of the larger and negative 9. Aha, it does create truth, and so I know that it's right. Okay, let's take a look at another one similar to that. And so what we're going to do here is we're going to say, like we did before, we've already taken the r, we have subtracted a negative 8, and the opposite would be to add a negative 8, or if you would prefer, then what I'm going to do is I'm going to look at it and I'm going to say, well, this is already adding a positive, which means I'm going to subtract, and I'm going to get the same thing either way. The bottom line is these will cancel, and I'll get that r by itself. And over here, combining up two digits that have different signs. Take smaller from larger, 8 from 6, 14 is 6. Take the sign of the larger one is positive, so my r is going to be 6. And again, we can check that. Take that 6, plug it right in here, and when I plug it in here, 6 minus a negative 8, now I really do need to look at it as plus a positive. And so 6 plus 8 gives me a 14. That creates truth because 14 is 14. I've got the same thing on both sides of the equal sign. Truth means it's right. That is the correct answer. All right, we just got 4 more and we're done. We're trucking right along, and I hope you're feeling good about this. I think you probably are. So what has already been done to this p? We've already subtracted a 3. The opposite would be to add 3. So I'm going to add 3 here. I'm going to add 3 here. That gets that p by itself. And now once again, I'm combining up two digits that have different signs. So I will take the smaller from the larger. 3 from 5 is 2. Take the sign of the larger, which is negative. Now, we can check it again. And remember, to check it, I'm going to go ahead and write this one out. I didn't write these out because I just didn't have space. I was running out of space here. But I'm going to write this one out. That means I'm going to take this negative 2. I'm going to put it right there where that p is. That will give me a negative 2 minus 3 equal to a negative 5. And notice here that I can look at it and say, well, they have the same sign. Or I can look at it and say that this is adding the opposite. Now I am combining up two digits that have the same sign. So I'm going to combine the digits. 2 and 3 gives me 5. I'm going to keep their sign. And sure enough, that creates truth. Because I do have the same thing on the left and the right hand sides. This is a true statement, and when it is, that means that's right. Okay. Now, I like this example because a lot of people get used to having that variable on the left-hand side of their equal sign. But it doesn't have to be on the left-hand side of the equal sign. The whole idea here is, I want this variable right here to be by itself. So I have to look at this and I have to say, what has already been done to that variable? Notice there's no variables over here, so I'm not going to worry about that side. I'm worried about this side, getting that a by itself. Now what's already been done is we've already subtracted a 92. So we have to undo that, and we have to add a 92. And whole pan balance idea here, if I add a 92 over here, I've got to add a 92 over here. And that gets that a by itself. And here again we've got the idea of digits with different signs. And we are combining them up by adding, which means take smaller digit from larger digit. 55 from 92 will be a 37. And then, like we said before, take the sign of the larger one. That 92 is larger, so we're going to keep its sign, which is positive. So my A is going to be a 37. And once again, we can check this one as well. Remember, all we have to do is take this 37, plug it right here where we see the A. So that's a negative 55 equal to a 37 minus 92. And when we take 37 minus 2, we're going to add the opposite. And now, once again, digits with different signs. So take that 37 from 92, you'll get 55. Take the sign of the larger, the 92 is larger, take its sign, and sure enough, that creates truth. The left and the right-hand sides are the same. All right, just two more. We've got this. So this one, a little bit more difficult because we have fractions and mixed numbers in there. But oh my goodness, we've done fractions and mixed numbers. You're very good at them. You've got this. So notice, here's where the variable is. That's what I want to get by itself. So just ask yourself, what's already been done to that variable? That D, we already subtracted a 3 5/8. So the opposite of subtracting 3 5/8 would be to add 3 5/8. So I'm going to add 3 5/8 here. I'm going to add 3 5/8 here. These will cancel out completely. That gets that D by itself like I wanted. And so on this side, I have to add those fractions. Now remember, what does it take to add fractions? Yes, you have to have that common denominator. I'm going to go ahead and slide this out of here. I'll put it back up, but I need some space now. So this 1/4 plus this 3 5/8, the common denominator is going to be an 8. So 1/4 turning it into 8s. This one's already there, so I'm feeling fantastic about this one. But I'm going to multiply the 4 by 2, which means multiply the numerator by 2. So 1/4 is the same thing as 2/8. Now remember, with these mixed numbers, you can either go ahead and turn this into an improper, combine them, and then take that improper and turn it into a mixed number, or you can look at this and say, this is 3 whole pies and a portion of another pie, and I'm going to throw this portion into that portion. So if I have 2/8 of a pie and 5/8 of a pie, that's 7/8 of a pie combined with the 3 whole pies. And there's the answer. Now, we can still check this one as well. When we go to check this, remember what that means is, take this 3 7/8 and put it right here where you see that D. So when I check it, I'm going to take that 3 7/8, I'm going to subtract 3 5/8, and what this tells me is 7/8 of a pie, take out 5/8 of a pie, gives me 2/8 of a pie. 3 whole pies, take out 3 whole pies, I'm only left with this portion of a pie. Now, does 2/8 simplify to 1/4? It sure does, because if I take 2 and divide it by 2, I get 1. 8 divided by 2 is 4. Yes, this is a true statement, and that tells me that is absolutely right. All right, let's get that one that I erased back up there. Now, you may feel like the one that was up there was kind of elementary, but people do get stumped on this one. Because what happens is they look at this, and the fact that that's a 0 just kind of throws them off a little bit. They're used to seeing a number over here, and so it throws them off when there is no number over there and it's just a 0. But remember, the whole idea is get this variable by itself. In order to get that variable by itself, I need to ask what's been done to that variable. We've subtracted 14. The opposite of subtracting 14 is going to be to add 14. I'm going to do that to both sides to keep my pan balance balanced, and 0 plus 14 is 14. And just like before, we can check this one as well. Put that 14 right here where that C is. 14 minus 14, what is it? It's 0, which is exactly what we have over here. Please understand that when you're checking these, and for instance with this check, when we plug it in and we do that, we're not indicating, well, the answer's over here on the other side. In all of these equations, that's not really what it indicates. Seeing this doesn't really mean that P minus 3, the answer's over here on the right. On this one, this A minus 92, it doesn't mean the answer's over there. That's not at all what it means. It's this concept of that pan balance. And remember, the pan balance simply means that that equal sign is the fulcrum in the middle of the pan, and the two sides are balanced out. That's what every one of these equations means. Every time you have an equal sign in there, it means this is this, and the two are balanced out. So like we said before, in order to solve your linear equations in one variable, when all you have to do, well, actually in any case, is your two golden rules. Keep that pan balance in mind and do unto one side as you would do unto the other side, and then do the opposite of what has already been done to that variable. You're going to reverse those order of operations, which that will come into play later when we solve equations doing more than just one step. Okay, so let's take a look at an application of being able to solve equations. In this application, it says that the equation c minus 4.6x equals 25 represents the number of television channels received by the average U.S. home X years after 1990. C stands for the number of channels that are received. How many television channels were received by the average U.S. home in the year 1995? Okay, so here is an equation that represents the number of television channels received by the U.S. home. Now notice that in that equation it says that this X right here represents the number of years after 1990. And notice that we are talking about the year 1995. So if that's the case, then what would this X be? How would you figure out what that X is? Absolutely. You would take your 1995 and you would take out 1990, and that would tell you that X is going to be 5 years in this particular case. So what I'm going to do then is I'm going to take this equation, I'm going to put that 5 right here where that X is, and when I do, that's going to give me C minus 4.6 times 5 equal to 25. Now I know that 4.6 times 5 is going to be 23. Whoops, that's mine, it's not equals, I'm sorry. And now I have an equation that I can solve. We just discussed that in order to get this C by itself, I have to undo what's already been done to the variable. We've already subtracted 23. The opposite would be to add 23. So I'm going to add 23 to this side, and keeping that pan balance idea in mind, I'm going to add 23 to the other side as well. That will get the C completely by itself, and on this side, 25 plus 23 will give me a 48. Now, because this is a real-world situation, this not only means that C is 48, but C is 48 what? Well, remember, we were told that C stands for the number of channels that were received. So 48 is going to be 48 channels. Now, we just need to double check. Did we answer what we were supposed to answer? It asks how many television channels were received by the average U.S. home, and we just figured out it was 48 channels. So yes, we did answer what we were supposed to answer. And hopefully this helps you to see a very good illustration of the need for being able to solve equations in one variable and equations that are linear, where and this is the simplest case where all you have to do is maybe add or subtract something from both sides. So I hope that helps.